One thing I think that you want, if you beats me in ever, I was still alive. Wait, did you do both of the?
Welcome back, everybody. Welcome back. Let's go on.
Oh, so
Quite a few are missing. I hope it's not because it's because recording kind of promotes not showing up to class. That's not the plan or the intention for recording it, right? Anyways. So we're going to finish chapter 25. I have one little piece, which is the dipole moment, and then we will start with we go on to chapter 26. There is no difference between them. There is quite a few things that we have already discussed. They are already in chapter 26. So the two chapters are really just, it's artificial that they're separate. So, okay. So does anybody remember what we were doing on the board, and then time kind of stopped us and we said we will start over with the same problem? Or yes. Or a dipole moment in an electric field, right? Yeah. And so the question was, how much potential energy is there? So before I go on, let me first let me just recap what we did as far as point charges, electric fields, electric potentials, and so on. So remember, for point charges, we had, let's say you have a charge 1 here and a charge 2 here, and they're separated by a distance r. There is a potential energy between them, right? And that potential energy, does anyone remember what it was?
K Q1 times Q2 over R.
Q1, Q2 over R, yes. And compare this to the force between them. Remember what the force was? It's K, the magnitude at least. Q1, Q2 divided by R squared, right? So, yeah. So that was that. And then if you have a point charge, remember with the electric field or point charge, the electric field, let's say I have a charge Q here, and at a distance R away, there is an electric field and an electric potential. The electric potential was KQ over R, and the electric field is KQ divided by R squared, right? And here is a question. What was the process that we did to go from force to potential energy?
You set the angle.
We integrated. We said the work done is F dot dr from the initial position to the final position. And since the force is conservative, the work done is equal to the change in potential energy is equal to the negative of the work done, right? So we integrated. And you can see it like it's kind of, when you differentiate, you get 1 over R squared. When you integrate 1 over R squared, you get the 1 over R, right? Up to a minus sign. Similarly, when you integrate the E field, you get the potential. When you take the derivative of the potential, you get the E field. Up to a minus sign also. We'll put that minus sign for the later. So that was that. And then for parallel plates, so this was for for point charges. For parallel plates, they look like this. You have a plus plate, a minus plate, and they're separated by a distance d. Distance d between them. Right? The electric field, of course, is in this direction. That's the electric field. We said the potential difference between the plates, if this is at 0 and this one is at the distance d, then the potential is just the magnitude of the electric field times d. Right? Electric field times d. electric field times the distance between the poles. And so now let's continue with the dipole moment and the potential energy. So the potential energy of a dipole in a uniform electric uniform means it's a constant value and it points in the same direction. Alright? Alright, so here's the, usually a dipole, remember it's a minus charge, a minus and a plus, and they're separated by a distance d, right? By a distance d, that's the dipole. So this one, each of them is charge q, so this one is, let's say, minus q, and this one is plus q, right? The positive and that's the minus. And they're separated by a distance d. And remember the dipole moment, P is just Q times D, right? So this is the definition of the dipole moment, right? So now we ask, what is the potential energy for a dipole moment in an electric field? So I'm going to draw my dipole moment like so. Here's the plus, here's the minus, and they're connected. And the distance between them is D. So I'm going to draw my x-axis this way, and this passes through halfway, and then the y-axis this way. So the distance from here to here is how much? From here to here.
D half.
Yeah, d over 2, d, yeah, and that's d over 2. Good. And so the angle that my dipole moment makes with the x-axis, I'm going to call it phi. Right, that's the angle that it makes with the x-axis. So if the dipole moment is like this, then it will remain like that. But now I will apply an electric field to it, an electric field to the right in the x direction. So my electric field is this one. Right, that's the electric field. It's to the right. So if you have a plus charge in an electric field that's pointing to the right, what does the electric field do to a plus? Pushes it further to the right. And what does it do to a minus? Pulls it further, and what happens is it will rotate. So, so here is, I'm going to draw my electric field here. That is the electric field. And the charge is going to rotate. So it used to be here, and this is here. It will rotate. I'm going to rotate it by a small angle d theta. It's so small that it's infinitesimal, but you can see it if I don't, if it's that small. So I'm going to exaggerate the rotation. I'm going to show the angle, the d phi that it's going to rotate by. So it's going to rotate, it will be here. Okay? It's here, so this is plus, and the minus will be here. Okay. We agree with that? So this is, this change here is d phi. That's d phi. It's tiny. So now, this plus used to be here and moved here, so it displaced from here to here. So the displacement is this one, looks in this direction. That's the displacement, and this is the angle between the displacement and the electric field. Now this angle from here to here is phi. So this angle here is what?
90 minus phi.
This is phi, and those two lines are parallel.
Oh, okay. That's phi.
Another phi, right? What do you call these two angles?
Complement.
Corresponding angles, yeah.
Corresponding.
Yeah, so phi here. And this one is 90 minus phi, right? This one, the orange one. This one, that's 90. 90 minus phi, all right? And the displacement is ds. Is ds. So the amount of work that the electric field will do on the plus charge, I'm going to write it down. So the W plus, or dW plus, because it's a small amount of work. So this is the amount of work done by the electric field on this plus charge, is equal. As usual, work done is the force. I'm going to write it not in dot product, just it would be force distance times the cosine of the angle between them, right? The force is the charge times the electric field, is QE, right? For a charge Q or an electric field, so it would be Q, it's positive Q, times the electric field, times the distance moved, displaced by an amount ds. So I'm going to call that distance just ds for now, ds. ds, that's the distance moved, times the cosine of the angle that the displacement makes with the force. The force is this way, right? The charge is positive, so Q times E is in that direction. And then the displacement is this way, so the angle that they make with each other is 90 minus P. So 90 minus P. And again, this is the magnitude of the displacement, and this is the magnitude of the force, right? This is the cosine of the angle between. Okay, so now, dW plus is QE, let's leave it as QE. Now, what is ds? I said, if you have an arc length, this is ds. This is d phi. This is ds. And this distance from here to here, it's from here to here. What is it, from here to here?
D over 2.
D over 2, thank you. And what's the relationship between arc length and, let's say, the radius of the circle?
S equals R theta.
R theta is S. So in this case, R is D over 2, and theta is just d phi, this small angle called d phi. So D over 2 times d phi. So it's D over 2, I left some space here on purpose, and then d phi. And then cosine of 90 minus phi is sine of phi. So this is just the trig identity, right? Cosine. Now, d phi, if you go counterclockwise, d phi is positive, right? The angle is increasing, the change is positive. If you go clockwise, the change is negative. So this technically, d phi is a negative number. So to make it into a magnitude, what do I have to do to it?
Absolute value.
Absolute value, or or stick a minus sign in front of it, right? Because recall, right? Everybody, nobody likes absolute values, right? The absolute value of x is equal to x if x is greater or equal to 0, and it's minus x if x is less than 0, right? Right? So, yeah. So now I have dW plus equal to minus 1/2 Q times D, this one, the Q times the D is what?
Dipole
Is the
moment.
P, yeah, it's the dipole moment. And then I have my E, right? And then I have my sine of phi. Sine phi. Oh, and d phi. Okay. That's the work done on the positive charge. Now what's the work done on the negative charge?
Okay.
Huh?
It's the same thing, but probably not.
It's the same thing, yeah. It's actually the same thing, even included, it's exactly this thing.
Oh, including the negative?
Huh?
It includes the negative?
It includes the negative, yes. And
Oh, okay.
and the reason,
Still gets smaller.
huh?
Because the DP between the angles gets smaller.
Yeah, dphi and the displacement, yeah, dphi gets smaller, so it's negative. The displacement is this way, the electric field is this way, so the angle is actually 90 plus phi. In that case, and after some trigonometry, you will arrive at the fact that the work done on the minus charge, and I don't want to go over it also, because I will take too much time. So dW on the minus charge is also minus 1/2 EE sine phi dp. And so So the total work on this dipole is the work done on the plus and the work done on the minus. So W would be dW, dW, the total work, is dW on the work done on the plus the work done on the minus. If you add them, you will get just minus PE sine phi dP. Now I don't want just dW, I want W, the work done. So what do you do to a dW to make it into a W?
Integrate.
Yeah, integrate. So the total work would be the integral from, let's say it was some initial angle phi initial to some final angle phi final. So integrate from phi initial to phi final. And you will get the following. W would be the integral. Put the minus PE here, minus P times E. The integral from phi initial to phi final of sine phi dphi. What's the antiderivative of sine?
Negative cosine?
Yeah, it's minus cosine, because derivative of cosine is minus sine, right? So it's minus cosine, but I have a minus sign here, so it becomes a plus, so it becomes PE times the cosine of phi evaluated between initial and phi final. And so you got W will be PE cosine phi final minus PE cosine of P initial. So that's W. But what is the potential energy?
Negative of that.
The minus of that. Yes. So the change in potential energy is minus W. So I'm going to write that in the next board. Okay. So delta U. Delta U equal to minus W. That is equal to minus PE cosine of phi final, and then so when you put a minus sign in front of it, this becomes a minus, this becomes a plus, right? So plus PE cosine of phi initial, and the change of anything is the final minus the initial. So this is equal to U final minus U initial. So that means U at any point is minus PE cosine phi. Okay? So U is minus PE cosine phi. And now you can write it in vector form. When you see the magnitude of two vectors times their cosine, you would get the dot product between those two vectors. So it's minus, right? If you have A, B cosine phi, the angle that they make with each other, so this is minus P divided with P. Now, why did I go through this derivation? Because the process of deriving it is important for you to understand. Okay. It's a good skill to be able, to integrate, reason through things. That's really the exercise. Not because this formula will appear every day. Okay. So let's do a quick example on this one. The example is, suppose I have a dipole. So here's the example. So let P, suppose I have a dipole, and it has a magnitude 6.2 times 10 to the minus 30. Units for a dipole are coulombs times meters, and E, the magnitude of the electric field is 1 times 10 to the 7 newtons per coulomb, right, 10 to the 7. And the question is, how much energy is needed to rotate this dipole? So here is the initial. So here is the electric field this way. Let's say electric field is this way, and let's say my dipole. That's the electric field, and my dipole is here. looks like this. Will the dipole go anywhere if I just leave it there?
No.
No, it's where it wants to be, right? The plus is that way, the minus is this way, that's the minimum potential energy actually. Yes, that's the most negative part of the potential energy. Now for me to twist it, to take this dipole and now force it this way. So I want to rotate it. Well, I'll be doing work against this electric field. So this is initial. And then finally, I would like to have it this way. Here's the electric field, right? I would like my dipole to look like this. Plus, minus, and then I orient it this way. I have to force it. So now it has actually more potential energy than the beginning, right? Because when you let go now, what happens to it?
It'll
It will
rotate.
spring back, right? It will go back to where it was. So it actually has higher energy here than here, higher potential energy. So the question is, how much energy must be put to do that? The energy would be, well, take the final potential energy, subtract from it the initial potential energy, find the change in potential energy, and that's equal to the work that you have done. Right? Because if I take, let's say this chalk here, let's take my reference to be 0 here. And let's say I lift the chalk. As I lift the chalk, now it's here, let's say it has 1 joule of potential energy. How much work did I do?
1 joule.
1 joule of energy, yeah. So, solution then? Delta U is U final minus U initial, which is this minus PE cosine phi. Minus or plus PE cosine of phi. I'm referring to this. Okay. What's the final angle?
90.
So cosine phi, what does phi refer to?
The angle between the four.
The dipole and the electric field, right? So the dipole is in what direction? This was in the test, right? It points always from where to where? Yeah, so the dipole is pointing this way. That's P. E is pointing, well, this way. So they're at right angles, so 90 degrees. So this is actually 90. What's cosine of 90?
0.
0. So this part is 0. This is 90 degrees. So 0. And how about the initial angle? Yeah, the initial angle is 0. The dipole points again from minus to plus, so it's this way. So it's parallel to the E. So the initial angle is 0. So we get just this. Delta U then will equal to P times E times the cosine of phi initial. Phi initial is 0 degrees, so cosine of 0 is 1. So you just get PE. And so, it's open. So multiply them, these two numbers here. 6.2 times 10 to the minus 30 times this, times 10 to the 7. So you get 6.2 times 10 to the minus what? 23. Yeah. Units, what do you think?
Joules.
Yeah. Any questions on that? Yeah.
So wouldn't it at final, wouldn't it have more potential energy?
The final, yeah.
Then how come it ends up being 0?
Yeah, because the initial has negative potential energy. Yeah. Yeah, so at 90, yeah, it has 0 potential energy. But at 0, it has negative potential energy.
Okay.
Well, you can't, because you have a non-conservative, I mean, it's, let's say it's me doing that work to twist it. Yeah, yeah. Yeah.
Is W, if delta U is equal to negative W, is that work done by the system or done by you?
this is, delta U is the new potential energy, right? That's equal to negative the work done by the system.
Okay, fine.
Yeah, so the work done by me is just W, equal to that. So I am the one who's doing it, but I don't know how to do it, but somehow I have to reach in and twist this dipole. Okay. All right, so if that's okay, I want to continue. And so to continue on, I'm going to do two examples, and they involve some integration. How to calculate the electric potential for a ring of charge, and then the electric potential for a disk of charge. And then we know the electric field due to a ring of charge and the electric field due to a disk of charge. And I'm going to relate the two to each other. So that's my plan for the next, let's say 30 minutes or so. Okay. So if, can I erase these two boards? Okay. And I'm going to, because I would need them too. So I'll be working on this one and then, yeah. So the problems. It's always hard to draw though in 3Ds, but hopefully I will be descriptive enough that you can follow my steps. So the first one, the electric potential, not field, electric potential due to a ring of charge. For a uniformly charged ring of radius r. Of radius r. I'm going to draw the ring so it would be clearly of radius r. So here is the, let me see if I can. So here's my best attempt. So the ring, I know it looks like an oval, but it's supposed to be 3D. So you're, you know. So here is the ring. Here is the z-axis. And the ring has radius r. This is r, capital R. Okay. That's my attempt to show 3D. So the ring would have a total charge capital Q on it. So since it has capital Q on it, then lambda, which is the charge per unit of length, would be the charge over the total length. The total charge is Q, but what's the length of the ring?
The circumference.
Circumference. 2 pi r, thank you. So 2 pi r. 2 pi r. So the question is basically, what is the potential at distance z here? So if this is z, the distance from here to here is z, what's the electric potential due to this ring? So as you may imagine, I think in the worksheet we did it for half a ring. For the class that meet me tomorrow, we will do that. Or actually, we did it. We already did. So we will do it for the full ring now. So here is the, let's say I have a charge, an amount of charge dq right here. A dq just sitting there. Then how much electric potential will it contribute here? Well, it's a certain distance away. This is called r. And it is r squared, capital R squared plus z squared. Square root. Right, that's the distance here, right? This is a 90-degree angle, so r squared plus z squared. Square root is the distance from d. So now, so the electric potential due to a single charge is kq over r. But I don't have a q, I have a dq. So I will not say v, I will say dv, a small amount of potential. A small contribution from 1 dq is this. So dv is equal to, it's kq, but instead of q it would be dq divided by r. Okay? K, of course, is the 1 over 4 pi epsilon naught. So K, I would keep it as K for now. Later I might switch to 1 over 4 pi epsilon naught. But for now, let's just say K. So K over R. Well, R is the square root of R squared plus Z squared. Okay. Now dq. How much dq is here? Is within this within this length, arc length of ds.
Or
RD theta. Yeah. So let's zoom into this. So look, here is dq there, and this is, we can call it d theta. This is r, and this is ds. So yeah. So the length ds is rd theta. So let me write it this way. dq, a small amount of charge, dq is lambda times ds, right? Charge per unit of length times the length that you have, which is ds. But lambda itself is capital Q over 2 pi r. So lambda is capital Q over 2 pi times r. Now ds is, we said, it is rd theta, right? So ds is r d theta. Notice the r goes away, so you get q over 2 pi times d theta. So instead of dq, I'm going to replace it with capital Q over 2 pi d theta. Okay, so dq, capital Q over 2 pi times d theta. Okay. That's dv. Now, my charge, I can start at this point, and I have to integrate every dq. So d theta, as I go around the loop, will increase from 0 to where? 2 pi. Yeah, will increase by 2 pi, from 0 to 2 pi. So to find z, I have to integrate this from 0 to 2 pi. So it would be, well, k is a constant. If you're at a fixed point on the fixed distance, z is a constant. The radius of the ring is constant. The charge of the ring is constant. 2 pi are constant. So all these, they'll come out from the integral. And then the 2 pi here. And we integrate the d theta from 0 to 2 pi. Now when you integrate from 0 to 2 pi, you just get 2 pi. And there is 2 pi sitting here, so they will just cancel. And you get the potential, V for a ring would be K, Q, over R squared plus Z squared square root. And if you like, you can write it as K is 1 over 4 pi epsilon naught, so you get 1 over 4 pi epsilon naught Q over R squared plus Z squared. That's the first calculation. Let's box it. This is a ring. Ring of charge. The next one would be a disk of charge. I would do it here. Any objections to erasing these two boards? I'm getting less bored. Okay. I'm going to erase this, right? I don't need it. Yeah. The plan for today, we already know. Now a disk of charge, uniformly charged disk. Potential for a uniformly charged disk. Okay. So let's say the charge density on the disk, charge per unit of area. What's the symbol for that? Usually we say charge over area is,
Sigma?
yeah, some call it sigma.
Eta?
Oh, shoot.
This one, right?
Yeah.
It's a symbol, it doesn't matter, but I would, because we're using a book, we would use the symbol the book uses. Although sometimes I use sigma myself. So, here is the disk. Again. This is the z-axis. And I'm attempting to find the electric field, not the electric field, sorry, the electric potential, the distance z from the disk. Now, what's the difference between a disk and a ring? A ring has charge only on the side, right? On the
Yes.
of the rim or whatever, and it's empty from the middle. But this is a disk, so it's understood that there is charge throughout, right? There's charge throughout this disk. Now, here's the idea. Just like with the electric field, a disk is made of many rings. So we take advantage of the fact that we calculated the potential due to one ring of radius r, radius in that case capital R. Let's consider one ring here within this disk, and it has a radius little r. So here's what I do. Here's the ring. Let's draw it with different colors. So here's the ring, and we have a certain thickness dr. So this is my ring. And my ring has radius little r here, and it has a thickness from here to here. That thickness is dr. Okay. Is that clear? Okay. So now, for this ring, it would have now, if you just had one ring, this would be V, right? But now I have many rings. So that, in that case, dV, let me write it, dV, would be the charge for a ring, the electric field for one single ring, which is 1/4 pi epsilon naught, and I'm going to write this formula here, or this one, doesn't matter. I will use the 1/4 pi epsilon naught for a reason that you will see. Q, instead of Q, the ring, does the ring have the entire charge Q of the disk, or it just has part of it? Part of it, so we're going to call it dQ. So we just, that capital Q, we're going to call it dQ, divided by the distance from the center of the ring, the distance from the edge of the ring to this point. So this distance. Now how large is this distance?
Little r squared plus z squared.
Square. So very similar to this one, but instead of capital R again, it would be little r.